Okay, this is our final review for the final exam continued. Okay, so another example, a study looked at 20 males and recorded their age and their VO2 max, which is an indicator of their aerobic fitness. Our data set is on Canvas there in that final exam module. It's VO2 as a text file. So I pull it up. I like to use Notepad to open it because it keeps all of the formatting the way it should be. Okay, so here's our data. Notice when you look at these, they're both numerical. So we have two numerical variables, or two quantitative variables. And if you come back to your formula sheet for the final exam, okay, you will notice that there is only one thing that has two quantitative options. Okay, and that is on the second page here. If they are both quantitative, that's the only thing you can do if they're both quantitative, is we're going to be doing regression. Okay. So that helps me get in the right frame of mind. I know, like, what am I trying to think about? What formulas am I going to be using? First, we want to know, is this going to be a randomized experiment or an observational study? Well, maybe before I answer that, I should figure out, like, which variable is going to be which. Okay, so it didn't say specifically, but I'm going to tell you that I think they wanted to use age as an explanatory variable. They want to use their age to explain how fit they are. So we'll do the VO2 as our response and age as our explanatory, and they are both quantitative. And so we said because of that, because they're both quantitative, the only thing we know how to do is regression. Let's see. So now that we know what our explanatory variable is, for it to be an experiment, we would have had to put people in each group, or we would have had to assign their explanatory variable levels. And I don't think we assigned people age. Okay. So I don't think we assigned people their age. Okay. So not an experiment. Okay, so that means it's going to be an observational study. Okay. What are the observational units? It was the 20 men. And what procedure should we do? Well, we know it's going to be regression. And what graph would be useful? Well, coming back to our formula sheet, it will even tell you, it'll say graphical summary, you want to use a scatter plot. Now, without actually looking at the scatter plot, I want you to guess, what do you think the correlation would be? Okay. Well, if you think about this, it's supposed to be measuring their aerobic fitness. And I would bet, okay, that if you looked at age and you looked at fitness, okay, at a certain point, like when you're young and stuff, you go up. But if we're only looking at adult men, I would think as you get old, it should probably be going down. Now, do you think this is exactly, like, is everyone going to be exactly on a line? Is every 40-year-old the exact same fitness? Or is every 50-year-old the exact same fitness? Definitely not. Okay. There are a lot of possible confounding factors. We have to look at people's, like, how much they exercise, their diet, their genetics. There's a lot of scatter. I would bet that there's a lot of scatter. So in other words, I think it's going to be negative, and I think it's probably going to be weak. Okay. So I don't know exactly what the number will be without looking, but it's probably going to be negative. It's probably going to be a fairly weak association because there are so many possible confounding factors. So many confounding factors that can affect fitness, like age. Sorry, age is our explanatory variable. We're looking for other variables like diet and exercise and genetics, etc. Okay, now let's guess our correlation from the plot. So looking at the plot, we have age here as our explanatory. We have our VO2 on the side as our response variable. Okay. If I was to draw in my nice oval shape, it does look like it's negative. We have a negative association. Okay. And I would say, if I was to draw a line through here, they're not very close to the line. I would say, again, it's pretty weak. So I would guess R is like 0.2 to 0.4 maybe, based on how weak it is. Now, what is the actual correlation? For that, I'm going to have to go click on my applet. Or let's scroll down to see. Nope, I didn't put it on quickly. So I'm not sure when my pausing and resuming got out of whack. So I think you have everything that I have written down. Like to guess my correlation, I was guessing it's negative. I think it's pretty weak, so I'm guessing from 0.2 to 0.4. To actually find the correlation, I didn't have it printed on here without it scrolling down quite a bit. So let's show you how to do it in the applet. If you bring up the applet, it's quantitative, it's the correlation regression. I came to my text file, I just copied everything. Now I'm going to come over here, I'll clear it, I'll paste, just Control V, use data. Okay. Now check, did it do your right explanatory response variable? It didn't. I want age as my explanatory. So I'm going to click this button and it will switch the order. So now age is my explanatory. And I click on correlation coefficient, so it's negative 0.527. Let's see. So R equals negative 0.527. So apparently I was very off when I guessed. It was quite a bit higher than I was guessing. Okay, so let's describe the association between variables. So form means is it linear or not? I think those look like they would fit a line very well, so I would say linear. My direction is negative. My strength is, I said weak, but it's actually like moderate based on that correlation, but weakish. Okay, it's not super strong. Any unusual observations, anything that doesn't seem to fit? I really don't think I see anything. I'd say no unusual observations. Okay. Now, just based on the association, which is negative, okay, then the correlation would also have to be negative. And the slope of the regression line must be negative. We know that those three things always match in sign. So if we have a positive association, then the correlation slope are positive. Or if we have no association, then our correlation slope would both be 0. Okay, or if one's negative, then all the rest are going to be negative. Now let's test if there's an association between age and VO2 max. The researchers suspect the older men would have lower aerobic fitness. So our null hypothesis is that there is no association between age and VO2. Okay. The alternative is we say there is a negative association between age and VO2. And if we want to do it in symbols, our null would be the, now remember this rho symbol? This is my population correlation. So that's called rho, it's my population correlation. So we think our population correlation would be 0 under the null. So if it's 0, there's no association, they're just kind of randomly scattered. My alternative then is that we think our population correlation is less than 0, that it's a negative association. Okay. How would we use everyday items to conduct a tactile simulation-based test of the hypotheses? Be sure to clearly describe how you find your p-value. Okay, so I'm going to pause and type it out so you don't have to wait while I type the entire thing. Okay, so if there's no association, that's like we're assuming that the VO2 scores were just kind of randomly assigned to each man, that it had nothing to do with their ages. So what we do is we write all the ages on one set of cards, and then we write all the VO2 scores on a different set of cards. Then we randomly shuffle and pair the cards together. So we're just randomly putting a VO2 card with each age card. So really their ages had nothing to do with which VO2 score they got. Then we find the correlation, and that's just one shuffle. So then we repeat that many, many times, and we find the proportion of times that we get a sample correlation of negative 0.527 or less. Because our alternative hypothesis here was that we wanted to find the proportion, or see if our population correlation was less than 0. So let's see. First, I pulled up my regression applet, or my correlation regression applet. And let's see, when I put it in, remember we had to change our response and explanatory. So we have our age here, we have our VO2 as the response variable. I put in 10,000 shuffles. This is my most recent shuffle. You'll see that the points look like they're just very randomly scattered. And my correlations are very close to 0. Okay, these are all of my different shuffled correlations. So I have 10,000 different shuffled correlations. Notice here, I do have to choose my statistic. The default here is slope, but I want to look at the correlations. And we're going to want to count the shuffles. I delete on purpose here. We want to do less than, because our alternative was a less than. Our hypothesis, or our correlation, which was negative 0.527. So we find our negative 0.527, which would be out here, and shade everything to the left. So what is our statistic? Our statistic is our correlation of R equals negative 0.527. What is the simulated p-value? Well, let's come back to the applet and actually count it, because I didn't count it yet. But I'm guessing it's going to be small just looking at that null distribution. So I show my shuffle options. I want 10,000 shuffling. Actually, this is the one applet that takes a long time, so let's just do 1,000. I have to choose my statistic to be correlation. I always forget that. We want to count our shuffles less than negative 0.527. Count. It looks like we're at 0.0060. So 0.006 as our p-value. So we got 0.006. What that means is that if the null is true, meaning that there's no association, then there is only a 0.6, if I want to change it to a percentage, 0.6% chance, 0.6% chance that we would get our sample statistic of R equals negative 0.527 or less. Okay, that doesn't seem plausible at all. So our conclusion, we could say things like the null is not plausible, because that's a small p-value, right? For my significance, it is a small p-value. So yes. Okay, do we have evidence? I would say yes, we have. That's less than 0.01, so we have very strong evidence that, and now you repeat the alternative hypothesis, that there is a negative association between age and VO2 max. What about cause and effect? So it's not a randomized experiment, so can't say cause and effect. What about generalizability? Did it say it was a random? If you look back up, it did not say it was a random sample. So we can only generalize to men similar to those in the study. Now, how would we find the equation of the least squares regression line? So for that, let's come back here to our applet again. So notice here's all my dots, and I want to put in a line. Well, if I put in a line, and I could put in a line myself, let's say this is my line, and I can drag it if it wants to cooperate. Much harder on this tablet. Okay, so there's a line. I don't think that'd be a very good line. So let's say this is my line. This is one possible line I could put in. Now I can click show residuals. So remember, your residual is the distance from each point to the line. Okay. What I want to do is I want to minimize these residuals. I want my line to be as close to as many points as possible. But the problem is this one's negative and this one's positive, and those will cancel each other out. So what I want to do is I actually want to square each one of these. And when I do the square of each one of these, I'll get a sum of squared errors. Okay, and I want to make that as small as I possibly can. So we need to find the line that minimizes the sum of the squared errors. Or remember, the error is the residual, or the distance, the vertical distance from the point to the line. Now, luckily, there are calculus-proven equations to make it so I don't have to try thousands of lines and then pick the best one. Okay. All we have to do is come back to our applet and click show the regression line. Let's get rid of my line. We don't need to see that anymore. Okay. So here's the regression line. It is the line with the smallest residuals possible, and you just read the equation straight off of that. So it would be the VO2, and they put the little hat on it to tell you it's predicted, equals 54.22 minus 0.3377 times age. Okay. Let's see, what does the slope mean in context? So my slope equals negative 0.3377. And if you're back in a math class, you'd say if x increases by 1, then y goes up negative 0.3377. So now because we're in a stats class, you need to actually write that in context. So you say something like, for each additional year, or if x goes up 1, so if your age goes up 1, for each additional year in age, so the x value is going up 1, we predict that the VO2 goes down about 0.3377. So we said down because it was negative. Let's see, what does the intercept mean in context? Does it make sense? Is it extrapolation? So the intercept equals 54.22. Okay, now let's see. So that means if x equals 0, y equals 54.22. Well, let's think about it. So what would that actually mean? That would mean for a man that is 0 years old, we predict a VO2 of 54.22. Okay, I would say this probably does not make sense. For one thing, that wouldn't be a man, that would be a baby. And that would be a baby. And they probably aren't that high. Which, remember, it's okay. Intercepts don't have to be logical. They just make our line fit well. Okay. What's an extrapolation? Well, let's go back up to our scatter plot here. Our scatter plot only goes from about 30 to 70-ish. So our data set only has age values from about 30 to 70. Okay. So we shouldn't make predictions for an age of 30. An age of 0. That is extrapolation. Now let's use our regression line to predict the VO2 max for a 32-year-old man. So basically we're just going to write down our equation and then plug it in. So my VO2, predicted VO2 is 54.22 minus 0.3377 times age. So we just have to plug in the age of 32. So this would be 54.22 minus 0.3377 times 32. And that would give me 43.41. Now let's use our regression line to predict the VO2 max for a 12-year-old. Okay. Well, I could just plug 12 straight in. Let's practice that just to practice. So 54.22 minus 0.3377 times 12. That would be 50.16. Okay. But notice, this is extrapolation. Okay, we don't have any 12-year-olds in the data set. The X values just don't go that low. So our prediction is probably wrong. Remember, the problem is we're like, okay, so here's my 30, here's my 70, and we might have a line right here, but maybe before 30, it actually looks like this, or maybe it goes like this, or up like that. Who knows what it is? You don't know what your line is going to be because you don't have any data for those X values. So let's find the residual for a 51-year-old man that has a VO2 max of 35. So this is saying basically that his X equals 51 and his Y equals 35. Okay. What we need to do is we need to find the residual, and the residual is always equal to our actual Y minus our predicted Y. Okay. And I do believe that's on the formula sheet right here. There's your residual formula sheet, or your residual formula. Okay. So I need to find my predicted Y. Okay. So for my predicted Y, I need to do my VO2 And I need to do the same thing we were doing up here. I need to do 54.22 minus 0.3377 times 35. So we get 42.4. Okay, so this is my predicted y. So for my residual over here, I do my actual y, which was 35, minus my predicted y of 42.4, which gives me negative 7.4. So that's my residual. Now, because my residual was negative, was my point above or below the line? It was below. You can also just look, my actual y was less than my predicted y. So the line is always your prediction. So here's my line, and there was my point. It was below it. So did the line overestimate or underestimate? My predicted value was higher than it should have been, so I was overestimating. And it's okay. Some points are overestimated, some are underestimated. We just want it to all kind of balance out. Okay. Now, let's find r squared. We can do it by hand. We just square our correlation r. So you take your correlation square. So we do the negative 0.527, and we square it. And it gives me 0.277. I can also find it with the applet. So coming to the applet, I just click r squared. And it gives me 0.278. Notice this little circle. Okay, it's telling you this light gray is how much error I have, how much I can't explain. And the dark gray is the model. That's how much I can explain with my model. So it said 0.278. It just rounded differently than I did. And now let's interpret it. Okay, so r squared is how much variation we can explain with our line. So we can explain about 27.8% of the variation in VO2 levels by their ages, or like with our line. Okay, that means we can explain about 30% of the variation. That's not horrible maybe for something dealing with humans. Humans have a lot of variation. The rest of the variation just has to do with all those other confounding factors of what was their diet, what were their genetics, how much did they exercise. And if I wanted to add a new data point, which one would change the equation of the line the most? Or like which one would be the most influential? So it's influential if it changes the line a lot. So let's look at, this was my original data set. Here's my line. It looks like it fits well. Here's my slope. That's really what we care about. There's my correlation. Now I'm going to add this person that's 50 years old. So there's 50 and VO2 max of 55. Notice my slope didn't change much. I mean, changed a little bit, but not very much. Okay. What about if I add a person that's 100 years old and they have a VO2 max of 20? Notice when I put that point is, it kind of just fit on that line pattern anyways. So like if you were to extend this, here's your 100 and 20, it was really just like right on the line. So adding a point that was on the line but farther away, actually my slope stayed about the same, but my correlation actually got stronger. Okay, and that's because I added a point that was already on the line, or on the existing line. So it might be far away, but because it was on the existing line, it actually just convinces it that the relationship is even stronger. We actually got a higher correlation of negative 0.64. Okay. But what if we had a man that's 100 years old and has a VO2 max of 70? So we still out there running marathons. Okay. Because he was so far away and we put him up high, notice what happened to my slope. My slope changed to positive. Okay, my correlation, again, changed to positive. So just one point can completely ruin your entire line. And that's an important part that you need to remember. You also need to remember that points with X values far from the rest can have the most influence. Okay, so if I had added like someone that was 50 and a 70 up here, it wouldn't actually change the line very much. Or like 35 and a point up there, it wouldn't change the line very much. Okay, but because it probably would have made more sense to draw here. So if I'd added the 70 here or the 70 here, it wouldn't change the line very much. But because I put this one way over here and the X value is so far from the rest of the X values, it's going to have the most influence. Now, let's do a chi-square test. Okay. So a researcher wanted to compare 3 types of asphalt. Pieces of each type of asphalt were randomly subjected to repeated loads at high temperatures, and the resulting cracking was analyzed. So 3 types of asphalt, and they either had major cracking or minor cracking. So what are the 2 variables? The first one is type of asphalt, which is categorical, with 3 categories. And the other one is how much cracking, or we'll say major versus minor cracking, which is categorical with 2 categories. And we only have one thing that lets us do more than 2 categories, and that is our chi-square test. So coming to your formula sheet, we're now going to look at these both categorical groups, and here's everything you need to know about it. So what procedure should we use? We want to use chi-square. And if you come back and look, we need a segmented bar graph or mosaic plot. Now, if all of our asphalts were all equally good at preventing cracking, what would you expect the plot to look like? I would think it would be something like, so here's your A, B, and C. And I would think all of their proportions of major cracking would be the same. So I don't know exactly how this breaks out, but all of the proportions should be the same across the 3 groups. Now, here's our actual data. What's our guess of whether, do we think that the asphalts are equally good? Okay. So we have one that's up here and one that's down here and one that's here. I'm guessing there's a difference. Okay, they don't seem to be equally proportioned there. You can look at the conditional proportions, 0.45, 0.26, 0.378. My proportions seem to be different. The sample proportions are different in each group. Now the question is always, how different are they? Could that just be due to chance, or is there something really happening in the populations here? Let's find the conditional proportions of the pieces that had major cracks in each group. So what we're going to do is we're going to go to type A. There were 26 that had major cracking out of 57. So 26 divided by 57. And guess what? That gives me 0.456. You could just read it right off of that. So for type B, its sample proportion is just 0.265. And for group C, we do 34 out of 90, so we get 0.378. But we want to know if in the long run, the 3 types of asphalt are significantly different. So our null hypothesis, the type of asphalt is not associated. So the null is always that there's no association, okay, associated with the amount of cracking. Or we could say the proportion of asphalt pieces that had major cracking is the same for each group. And that would make more sense if we wrote it in symbols. We could do the population proportion in group A would be equal to the population proportion with major cracking in group B. And that would be equal to the population proportion with major cracking in group C. We want all those population proportions to be the same in the null hypothesis. The alternative is that the type of asphalt is associated with the amount of cracking. Okay? And you say the proportion of asphalt pieces that have major cracking is not the same for each group. Now for the alternative, there's no good way, because it might be that one is different from the other 2, or it might be that they're all different. And there's not a good way to write that in symbols that we want to do. So we'll just say at least one of the population proportions is different from the rest. Okay. So now what is our statistic? So remember, the problem with the chi-squared is we had 3 different proportions, and so we couldn't just look at one difference. So we actually have to use our chi-squared test statistic. Okay. And so here's my simulation stuff down here, and then we'll write our answers up above. So you have to click this box for enter table, and you have to choose what size. So I wanted a 2 by 3, so I put all of my data in, double check the totals to make sure you put in right. Don't forget to use table. And I like to click show table here. And choose your statistic to be chi-squared. You have to do that. And I like to click show chi-squared output. So here's my table with my proportions. And here's my statistic for chi-squared equals 4.126. So chi-squared equals 4.216. I apologize, 4.126. Let's see, what is our simulation p-value? So coming down, a few things I showed you. You could do mosaic plot, or you could just leave it as segmented bar graph. Make sure your success is what you want. We were counting how many had major cracking. You don't usually have to worry about changing that here. I'd put in 10,000 shuffles. You can see on my most recent shuffle that my groups look very similar. And my shuffled chi-square is pretty low, okay, a lot closer to 0. Make sure you have a chi-squared as your test statistic, and we want to count samples greater than 0.4126. For a chi-square test, it's always samples greater than. It's always going to be greater than for a chi-square test. Okay. So my simulated p-value is 0.1324. So that means that there is a 13.24% chance that we would get a chi-square statistic of, what was it, 4.126 or more. It's always more, okay, if the null hypothesis is true. So if there is no association, okay, that seems quite plausible. Okay. What is our theory-based p-value here? So to do our theory-based p-value, we just click this overlay chi-squared button, and it will tell you your theory-based p-value right here. So this is my theory, this is my simulation. So 0.1271. I could also click right here. Not working. I could click this show chi-squared output, and it will also give you your theory p-value here. You can read off either spot. Were we supposed to use the theory-based p-value? In this case, yes, because each of these counts, you don't look at the totals, you just look at the counts. Each of the counts is at least 10. So each of the cell counts is at least 10. So yes, we could use the theory-based approach here. On the formula sheet, again, you'll see that we did put on your validity conditions, at least 10 observations in each cell. So what is our conclusion? Well, we had a big p-value. And because we had a big p-value, we would say we have no evidence that there is an association between type of asphalt and cracking. Okay, I was kind of guessing maybe there was, but our p-value wasn't that small. For generalizability, did it say where these samples came? Okay, so it didn't say that they were random samples, so it didn't say random sample. So only generalize with caution, or only generalize to samples that are similar, things that are similar to what was in your sample. What about causation? It did say that they were randomly assigned. So we can say cause and effect, but that's not really interesting because we said that there is no effect, there is no association. Last one here. A computer manufacturer has 4 suppliers of electrical circuit boards. Random samples of 200 circuit boards are taken from each of the suppliers, and they are classified as being either acceptable or defective. Data, and it's in the data set. Okay, so I want you to think about this. We have 4 suppliers. So our explanatory variable is the suppliers with 4 categories. And then we're either acceptable or defective. So my response variable is acceptable or defective. So that is 2 categories. Okay. So because we have more than 2 categories in one of those, we're going to have to use the chi-square test. Okay. And to find these confidence intervals, when you come back up to the simulation, I guess it's not on there. If you come to your multiple proportions, that's what we do for our chi-square test. At the very bottom right here, there's this button for 95% confidence intervals for the difference in proportions. That's how you get these confidence intervals that I'm showing you. So now that we've said all that, they found the 95% pairwise confidence intervals for us. And the suppliers were just the A, B, C, and D. So these 4 categories were A, B, C, and D. Not very exciting category names. So these are for each group. So A compared to B, A compared to C, A compared to D, B compared to C, etc. It's all of the possible pairs that you could have. And these are the confidence intervals for the differences in their population proportions. So these are the pairwise confidence intervals for the difference in their population proportions. So which pairs of groups have statistically significant differences? You're statistically significantly different if 0 is not in the interval. So which pairs have 0 not in there? So it looks like this one. So A versus C. And this one, B versus C. And this one, C versus D. And, oh, I told you which one would you recommend to your boss, but I wanted to show you the actual plot. So I'll add the actual plot to your notes before you take it. But let me find the data set. So we want our circuit boards, and I'm going to just copy all of that data. I come to my applet. Let's see, let's clear that. I click Use Table. And so here's my bar graph, and our success was that they were acceptable. And looking at it, you can see that C seems lower than all of the other groups. Does that make sense then? Each of these intervals that was statistically significant from the others included a C. So looking at the bar graph, C is lower than the other groups. So C is lower than the other groups. So C is probably the one that we want to get rid of. The rest of them probably don't matter, but C is lower than all the rest. Okay. Let's interpret the following intervals. Let's do A versus B. So we could say this a few different ways, but we could say something like the proportion of acceptable boards is, now let's see, for A versus B, we start at negative 0.022. So we'll do 0.022 less to 0.072 more for the A versus B. Okay. Or you could say something differently. You could be like boards in group A. Oh, let's do A versus C now. So boards in group A are, let's see, so for A versus C, we're 0.18. So we'll say 0.18, we can say more likely, so it has a higher proportion or higher probability. More likely to be acceptable. So 0.18 more to 0.32 more likely to be acceptable than boards in group C. And let's just write these numbers here. So this was negative 0.022 to 0.072. And A versus C, that was our 0.18 to 0.32.